Today we are going to discuss, I think this is question number 5 and 6, not 4 and 5, from the question paper of 2020 group theory. So yesterday we have discussed the question number 3 and 4, I guess. And the rest thing, let us see how we can proceed further. So question number 5 is that let H be a subgroup of a group G, and then we have been given a mapping from coset, from a left coset to right coset. This is a left coset and this is a right coset, and it's a bisective. We need to prove that this map is a bisective. Okay, and then what is there? Can the same be said for the map defined by AS to HA, that is a left coset to right coset. Okay. So essentially there are two mappings. One we need to prove that it is bisective. Bisective means this is 1, 1 and on 2. And there is another mapping which takes AH to HA, and we need to prove that that mapping is whether that the same thing is true for this mapping or not. That is whether it is bisective or not, or whether this kind of function we can talk about or not. Okay. And the next part is that if G is non-abelian group of order 8 with the center is non-identity, then we need to prove that order of center is 2. So there are 3 parts. So let us see them one by one. Solution. So what we have been given that H is a subgroup of G. Okay. So let G be a group, and we have been given H as a subgroup of G. Now define a map, for example 5 from actually they are defining a map from collection of all left coset to the right coset. Okay. So or we can write like this also. Let us consider suppose S and T be the collection of all left and right cosets of H in G respectively. That is, S is a collection of all those, for example, left coset for A belongs to the group G, and T is a collection of all right coset for A belongs to G. Now we can define the map is given from left to right coset. So let us define a map phi from S to T by how it is defined that because S is a collection of all left coset. S is a collection of all left coset. So phi takes left coset onto a right coset, and the right coset is given by A inverse. So the same element A inverse of this is with the help of inverse of this A, that particular element A, we are defining the right coset here. Fine. So now we need to prove that this function is 1, 1 and onto. That's all. So that means this is surjective. Okay. So now we claim. Now we claim that phi is 1, 1 and onto. Phi is 1, 1 and onto. And of course, you can also prove that this is a well defined. You can also prove this is well defined. Here, phi is well defined as how we prove that a function is well defined. It means that if you are taking that if there are that is two distinct elements of S should have this sorry, two, if you are taking any two elements which are same, so their images also is going to be same. Okay, so it means AH equals to BH. Fine. If you are taking like this, so if you apply AH and phi equals to BH, so by definition, this is going to be there, or else we can say like this. Okay, sorry, what happened? Or we can say like this that if AH and BAH equals to BH, so this implies that AB inverse belongs to H. You know that the two left coset are equal if and only if this holds. Okay, AB inverse belongs to H, and this implies that A inverse and then inverse, because H is a group itself, so it inverse इसका exist करेगा और इसके inverse का inverse exist करेगा. So we can write A as this, and then B inverse belongs to H, and this implies that H A inverse equals to H B inverse, and this means that this is an image of AH. This is a image of AH, and this is equals to image of BH. So this proves that phi is well defined. Now we can try to prove that this is onto. Let us see how we can prove this is onto. I think sorry. Okay, they are writing bisective. So for onto, we can take a letter Y belongs to T. That is the collection of all those right cosets of H in S, H in G. Then Y equals to HA for some A belongs to the group G. And then we can, this implies that then we can write HA, this is equals to HA, and A we can write A inverse of A inverse. Fine. So this implies that if we apply phi from on both sides, left and right side, so we are going to get phi. No. Just a minute. Okay. So fine. So I think we need not to write like this, or we need not to write like this. So once we have A inverse here. Okay, we have A inverse and its inverse. Fine. So corresponding to each element y in T, corresponding to each element y in T, we are able to get A inverse here. A inverse. A inverse will be where? By definition, A inverse will be element of course G, such that phi of H A inverse H equals to H of A inverse. I think you got this. So once we have some element here, then we can write it as like this: y equals to HA for some A belongs to the group G. And then HA we can write like this. And once we can write like this, then of course A inverse, because G is a group, so inverse also exists. So we can talk about this left coset, and if we can map this to this, okay, by definition. So now see 1, 1, 1. How we can prove this is 1, 1. To show this is 1, 1, we need to show that if images are same, then the pre-image is also going to be same. So for any not f, but we need to write phi. Okay. So phi of ah, or we can write let phi of ah equals to phi of bh. So this implies that by definition, by definition, how we can write uh, uh, this means that H A inverse equals to H B inverse. So they are right cosets. Okay, they are right cosets, and two right cosets are equal if and only if you can write A inverse. Okay, A inverse and inverse of B inverse belongs to H. In one sense, you can write it. Sometimes you may get confused how we can write like this. So you just see that was just for the sake of memorizing and telling. So if we multiply on both sides by B inverse here, okay, yeah, by B inverse here, or by B here, both side on by B. So we can have B here, so it becomes identity. Here what we get here A inverse, and we get B. A inverse B, and B we can write B inverse of B inverse like this. So this should be below, this should be a member of H. So like this you can memorize. Okay. Okay, so this belongs to H. Now, because this is the element of H, so by definition of equality of two left coset or right coset, right coset, uh, they are right coset. So this holds if and only if this holds, and this holds if and only if AH equals to BH. Now, from this how you are getting, because B inverse of B inverse is B. So this belongs to H. Okay. So you just need to take, you keep it here, and then if you are multiplying on both sides from here, on left side, so suppose you are multiplying here, okay. So it means B belongs to A as something like this, okay. So H, if you are multiplying H, so H times H is equals to H. This is going to be H only, okay. H equals to H. So like this, you will be getting. So this is a way of memorizing. Otherwise, you may get confused sometimes. Okay, But if you are remembering or know the if you are knowing the technique, then there is absolutely no problem. So this way, we have seen that if images are same, then their pre-images are also going to be same. Okay, so this proves that this phi is bisective. A few more things uh, you can note it down that bijective means bijective means 1 1 and onto. Injective means 1 1 map, and surjective means onto. Okay, so these terminologies you may remember. So next part is that they're asking that can the same be said for this map AS goes to HA. Okay, so initially in the first map they are writing here A inverse, but here they are keeping the same element. Okay, so let us see if in fact this cannot hold, because you know that without equality, without equality of elements, that is suppose you have two elements A and B, and you are finding out uh, coset, right coset for example, or left coset. So even if they are distinct, H there may be happen H equals to HB. This is possible also. So there is a big question whether that is equal or not, and obviously this suggests that that cannot be true. Okay, that same cannot be true in case of the map AH map to HA. Okay, so for this we need to have certain example. In fact, let us see some counter example for this. Uh, uh, the above conclusion, sorry, above conclusion is not true in case of map phi. Okay, phi maps AS to uh, phi maps AS to HA. Okay, so let us see, consider the example in support of this. Consider the group S3. In S3 we have identity, and 1 2 2 3 1 3 1 2 3 1 3 2. This is a group, and let us take a subgroup H containing identity and 2 3, and you know that this 2 3 is self inverse. 2 3 is self inverse because it is a two cycle. Fine, so this is self inverse. E identity is also self inverse. Okay, then clearly H is a subgroup of S3. Subgroup of S3. Fine. So let us take elements. Okay, let A equals to, let us take A equals to 1 2 and B equals to 1 2 3. We are taking these two elements 1 2 3 and 1 2. You can take this also, but the thing is that we need to give counter example, so suitability need to be checked. Fine, suitability need to be checked. Then just compute A inverse B. A inverse B is equals to A inverse, we can write 2, 1, and B is 1, 2, 3. And once we multiply these two, take product, so we are getting 2, 3, and this belongs to H. And A inverse B belongs to H here. Okay. So the left corresponding left coset is going to be equal. Okay. So AH equals to BH. That is 1, 2, H equals to 1, 2, 3, H. You see that they are distinct. They are distinct. This 1, 2, and 1, 3, 1, 2, 3. They are distinct, but the corresponding left coset are same. Okay. And also uh, AB inverse. AB inverse, once you compute this, you will be getting 1, 2, 3, and 3, 2, 1. For inverse of this, just put them in the reverse order, 3, 2, 1, right, like this. Okay, 3, 2, 1. So this will give us 1, 3, and 1, 3 doesn't belongs to H. So this implies that HA is not equals to HB, because this holds if and only if. This is the condition for if and only if. I'm using the result AB inverse belongs to H if and only if HA equals to HB. Okay, so this result in case of right coset we are using, that is H1, 2 is not equals to H 1, 2, 3, like this. Okay, so this means but let me write something more to make it clear. Okay, so what we have seen that in these cases uh, we are getting different kind of thing. If you are computing left coset and right coset, once they are becoming equal for the same A and B, but in other case they are not becoming same. It means that the same functions or same element can have more than more than one image. Okay, more than one image. But let us see. So here, if you see here, so what we have AH equals to BH. So let us apply phi function, if function phi AH, and this is equals to BH. This just apply this phi function on both sides. And by definition, this is going to be HA. This is equals to HB. Okay, HA equals to HB. HA equals to HB. When they are equal, left cosets are equal. So by definition of phi, if we are assuming that that is true, the definition of phi, new definition of phi, which maps phi AH to HA. Okay, we are using this definition. So this equals to AH equals to HA equals to HB. But you have seen just here, HA equals to is not SB. Fine. Okay. Or we can write this holds if and only if AB inverse belongs to H. But this is not true, which is false. Okay. This is false. Okay. You make write as false. C star this equation. Okay. See this equation. So this kind of mapping, that is not possible, or we can say that thus phi is not well defined. And when we say that phi is not well defined, it means phi is not a function. Phi not a function. It means that a same element can have more than more than one images. Okay. So many elements can have a single image. That's all right, many to one. But one element cannot have more than one image. Okay. So that will not be counted as a function. Okay. I think it's all right to you. Let us see what is there. Okay. Then the next part is there. If G is non-abelian, group of order 8. with center is non-identity, then we need to prove that order of center is equals to 2. So let us see. Let G be a non-abelian group. Okay, non-abelian. G be a non-abelian group. G be a non-abelian group, and we have been given that the order of G is 8, and the center of G is not equals to identity. So this implies that order of ZG cannot be equals to 1. Now, since center of a group is always a subgroup of G, so by Lagrange's theorem, order of ZG, what is the possibility of this? Is 1, 2, 4, and 8. 1, 2, 4, and 8. Okay. Here, order of ZG cannot be 1 because ZG is not identity. Okay, this cannot be 1. And order of ZG is not equals to 8 as G is non-abelian. All right. If its order is 8, then it means what? That every element will be commuting, that is all element of G will become the element of center. Okay, in case of if G is abelian. So there are two possibilities are discarded. So it cannot be 1 and it cannot be 8. So now remaining possibilities are 4 and 8. So now we are left with two possibilities. Namely, order of center is either equals to 2 or 4. Here you can consider or. Fine. So either it is 2 or 4. So if we can prove that some 2 is not possible or 4 is not possible, so it will take. So we come to the conclusion that either 2 is possible or 4 is possible. So let us assume that if, uh, for instance, let us assume order of the center equals to 4, then since this center is always a normal subgroup of the group, so we can talk about this quotient group G by ZG. We can talk about, and therefore the order of this is equals to order of G divided by order of center of G. And this is equals to 8, and because the group order of group is 8, and we have assumed that it is 4, so this is equals to 2, and 2 is a prime number. 2 is prime. 2 is a prime number. Okay, so you know one result that if order of a group is prime, then what you can say about the nature of that group? Do you remember? So this implies that the order of center of G, this is equals to 2. This is a prime. Okay, so this means that every group of prime order is what? Hello. Every group of prime order is cyclic. And you know that there is one result if Z by G by ZG. You can note down if G by ZG, that is center of group, is cyclic, then G has to be abelian. Okay, so this implies that G is abelian. But this is a contradiction to the fact that fact or the state, the assumption of the theorem or proposition of the theorem that G is non-abelian. But G is given to be a non-abelian group. Non-abelian group. Okay. So we must have. So our assumption is wrong. Okay. So we must have order of center of G is equals to 2. So can you tell me what is the possibility of this group they are talking about? This should be of order 8. This should be non-abelian also. Okay. And in center it should have have 2 elements exactly. Do you know? Do you remember any example? Hello. What about Q8? What about Q8? You have plus minus 1, plus minus I, plus minus J, plus minus K. So order of Q8 is 8. And this is not abelian. Okay, not abelian. Fine. Not abelian, and order of Q8 is 8. And in center of G, that is Q8, in center of Q8, elements, which element commute with other elements of G, namely there are only two, 1 and -1. Okay, so this example supports our argument. Fine. Okay. You can similarly you can actually your proof completes here. I'm just giving some more thing to you. You can let G equals to, there is, you can try out another group, D4. Okay, in D4 you have 8 elements, R0, that is identity, and then R90, R180, R270, horizontal flip, vertical flip, diagonal, and another diagonal. So they are. So can you find it out now? Of course, in D4, it has 8 elements. And can you tell me what is the center of D4? So this is a question. This is exercise to you. You find the center of D4.
R0.
Hello. Yeah, R0. One identity. You see, center is never empty, because at least one element, identity element, is going to be there. Okay. So we are interested in other what we say that other elements which commute with other elements of group. I think one R180 may be there. Identity and R180. Rest you can check it out. I guess there will be 2 elements only, but still you can check it out. Okay. or you can see the Cayley table for this, where we have discussed. Okay, so from there you can guess, or you can exactly you can find it out which element come with other element. So two elements in easily I think we can keep R0 and R180. Rest you can see, and you can tell me in other class. Okay, so let us see next question. Let n be a normal subgroup of G and M be a normal subgroup of N. Okay, if N is cyclic, then we need to prove that M is normal subgroup. Okay, so thing is that uh, let G be a group and N is normal in G, N is normal subgroup of G, and M is normal subgroup of N. So M is normal subgroup of N. Okay. So one may ask now that whether M is normal in G or not. Okay, M is normal G on in G or not. But an additional condition is given. Of course, if you're directly asking without giving any condition, so M cannot be need not be normal in G. I have given you example during the class. But they are imposing another condition on N, that N is cyclic. Okay, so suppose, or let N be cyclic, then there should be some generator of it. Okay, so let us assume that this is generated by what we need to prove. Let me write here first. Claim. What we need to prove? We need to prove that M is normal in G under the condition that N is cyclic. Okay. Suppose that N is cyclic, then in this case, let me write here something, and let N be cyclic, and this. Okay. Then we claim this. Okay. So if N is cyclic, then there should be some generator, and this is equals to a to the power k, where k belongs to the set of integers. Fine. So now, because M is normal in N and N is normal in G, so M will be subgroup of N and N is also subgroup of G, like this. So M be a subgroup of N and N is going to be a subgroup of G, and at least in case of subgroup we can write like this. So this implies that this is a subgroup of M is a subgroup of G. So to prove that M is normal in G, what we need to prove? We need to prove some element, for example, M in capital M. So M and G in capital G, in capital G, M, G, M inverse be member of M. Like this we need to prove. To prove that, in order to prove that M is normal in G. So let us assume that let us assume that X belongs to capital M. Okay, because M is a subgroup of N, so M will be contained in N. So then X is also member of N, and because N is generated by A, so A generates the group like this. K belongs to the set of integers. Okay, so this implies that X equals to A to the power T for some integer T, for some integer T. Now consider xg inverse x. Sorry, I think. Okay. I think something. Okay, let us see here. Consider G inverse. G inverse. Here we, I think I did some mistake. Here we should write M G inverse G. This should be member of, this should be member of capital M. Okay, I'm sorry for this. So let us consider this. So we can write uh, this as G, and X is nothing but a to the power T, and then a G inverse. So we can write it G A and G inverse to the power T. This we have seen. Okay, so suppose this is number one, equation number one. Okay, now since n is normal in G and A belongs to n, so this element A G G A G inverse should be member of n. Okay, and n is generated by A, and this is a collection of all those elements like a to the power k, and k belongs to a set of integers like this. Okay, so this implies that G A G inverse is going to be some power of A, and let us say R, for some R belongs to the set of integers. Okay, so from here, how we can write G X G inverse equals to, in place of this, we can write a to the power R. So we have a to the power R times T. By using index rule, we can write like this. Okay, for some R belongs to the set of integers. Okay, so now this is of the form what? A to the power some power. A to the power some power. Of course, a to the power T is what? X. So this is equals to x to the power R. X to the power R. And X is a member of M, and N is a subgroup. So this would be a member of capital M, as M is a subgroup of G, and X belongs to capital M. So this implies that G X G inverse belongs to capital M. This belongs to capital M. And therefore M is a normal subgroup of G, like this. So this completes the proof. Rest, let us see what else is there. So by an example that a conclusion fails if n is not cyclic. Okay, so if n is not cyclic, then we need to prove that that conclusion does not hold. Okay, so conclusion fails if n is not cyclic. So for this, consider G equals to D4. In D4, we have R0, R90, R180. D and D dash. Okay, and let us consider subgroups. Its subgroups. N equals to E R0 horizontal and vertical flips. This is nothing but you can see that this is going to be K4. Okay, and M equals to E and H. Okay, E and H. Here, order of each element in N is going to be sorry. This equals E equals to R0. R, I think, okay. E, and this should be R90. Okay, like this. So these three elements has order 2, and of course they are self-inverse. Fine. S has order 2, identity has 1. Here identity also has 1. Okay. So n M is normal, or we can say n is a subgroup of N is a subgroup of G and M is a subgroup of N. Sorry. Since G by N, order of this index, we are computing index. We can try like this: G by N, G by N. The index of N in G. This is equals to what? Order of G by order of N. So order of G is 8 by 4. This is equals to 2. So if the index is 2, it means that N is normal in G. So every subgroup of index 2 is normal. This is sufficient condition. Okay. And N is normal in G. And also index of N is index of M is N in N. Here should be N. Here M. Okay. So this is equals to also 4 by 2. This is equals to 2. This means that M is a normal subgroup of N. So all requirement of the result or assumption is fulfilled. You see that what is there? N is normal in G, M is normal in N. Okay, and N should be cyclic. Then prove that M is normal in G. Okay, so let us see. So M is normal in G, N is normal in G. Okay, so but and also here, in N. Okay, but here M is not normal in G. Okay, so this is the example, and not normal in G. Note that N is not cyclic. Okay, so for this we can try to find out order of E is 1, order of R90 is going to be 4. And just a minute. I think we missed something here. Should be R180 or what? Here should be R180, not R90. It should be R180 because in that case it becomes self-inverse. So please note it down. This should be R180. Otherwise, there will be an element of order 4. And if you are keeping R180, then it will not be a group. Okay. So let us order of identity is 1 and order of 180 R180 is equals to 2. And you know that horizontal and vertical flips, they have order 2. So there is no element of order 2. Therefore, so of order 4. So there is no element in D4 of order 4 in N. Okay, so N is not cyclic. Fine. So the result was that so if N is not cyclic. Okay, so if N is not cyclic, here N was chosen as it is not cyclic. In that case, M is need not necessarily be a normal subgroup of G. which need not be a normal subgroup of G. Fine. Okay. This part you can attempt by yourself. If I is a homomorphism from a finite group G to finite group G bar, phi G divides the greatest common divisor of G and G bar, order of G and G bar. Okay. You can try it out, or we can cover it in the next class.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.